All right, we are back for part 2 of chapter 8. But before we get started with part 2, I wanted to go over that small example where I got a tiny bit confused, but I think it was just a typo, and that's why. Let's look at this example one more time. This is the parameterized data declarations. And we saw that there is a data declaration for maybe, which allows us to take up type parameter A and indicate that the value for this data type is either nothing, which usually would correspond to a error, runtime error, or if there's no runtime error, we will indicate that by just a. Okay, so these are two constructors, nothing constructor and just constructor. The nothing constructor does not take any values as its own parameters, and this is the value. So nothing is a value in the maybe a type, and nothing would usually indicate something went wrong at runtime. Okay, and just a would be a value under the maybe a, indicating that yeah, nothing went wrong, and the actual value is this a which is sitting next to the just. Okay, so this is a way to take any type a and introduce um, the possibility of handling errors on that type, okay, by saying that, okay, we have a maybe a type, okay, so you can think of it as a container which contains a inside it, okay, or just a prefix saying that, oh, maybe it's an a, maybe it's not, okay, that's why we use the word maybe here, okay. So maybe is a type, maybe is technically in the theory, it's much more than just a type constructor here. But for now, let's say it's a type constructor. Maybe it's a type constructor which takes an a as input and returns maybe a as output. Okay, so it takes a type as input and returns a type as output. Okay, type constructors. So these are a little bit unusual, but they behave very much like functions, and you'll see that at the higher level, these are actually treated as functions at one meta level higher than the usual functions. Okay. All right, so maybe a equals nothing or just a, and the deriving show is just to do a default printing or converting to string. Okay, nothing represents failure and just a represents success. Okay, and the example I got confused a little bit about was the safe head. Okay, yeah, let's quickly look at that. Given a list A, we want to find the head of the list. Okay, which is the first item in the list. And we want to protect ourselves against the error situation when the list is empty. Okay, so we could define the signature of safe head, which is a different function than the usual head. Head is defined in the prelude, and head would fail on an empty list. Okay, you get a runtime error. Okay, and we want to protect against that runtime error here. Okay, so let's say that our new function is called safe head, which takes a list of A, but now instead of returning an element of type A, we will return an element of type maybe A, okay, or a value of type maybe A, okay. And the definition seems quite obvious. Safe head of empty is nothing. Safe head of excess equals just of head of excess, okay. All right, because in the second equation, we are assured that the input list is not empty. Okay, why? Because we have a previous equation which takes care of the empty case. Okay, so that's why the excess is assured to be non-empty. So head of excess would be a valid element, the first element in the excess, and we just add the just prefix constructor in front of that, and we can return a value of maybe a. Okay, so that's the right definition, and it seems to work. So if I run this cell and run that cell, I get the correct answers here on safe head of empty is nothing, and safe head of 1 to 3 is 1. I think the place where I got confused was here. Okay, I was trying to say that okay, if you look at this pattern is the empty, and usually in a recursion for a list we will say x colon xs here. Okay, so I was trying to do that last time, so let's go ahead and do it, x colon xs, but I think I went ahead and mistyped just of head of xs or something like that. Okay, I don't remember what it was, but that was in my hurry I typed something else on this side. Okay, but we know that x colon xs is matching the input list, and x is the first item, and XS is the rest of the list. Okay, and also this is not non-empty, right? Because empty case is already covered by that. So this is non-empty, and X would be the first item. And since we already have access to that first item, we just say, oh, just X is the answer. Okay. I think last time I just messed up something else here. Anyway, when we run this, we get the nothing for safe head. I call it safe head 1. Uh, for the empty list, I get nothing. And for the 1, 2, 3, I get just 1. Okay, so everything well and good. Okay, all that ends well, ends, oh, I forget that saying, but whatever it is. Okay, so we did clarify that small confusion we had last time. Okay. All right, let's get earnestly on part 2. Let's look at the table of contents here. We will talk a little bit about how one goes about deriving the subclasses. Remember, we have type classes, and we can say that another new type can become an element of this type class. How do we do that? So just some basics in the syntax. Okay, and then we will go ahead and try to build 2 different applications, one called a tautology checker and the other one called abstract machine, okay? Using the ideas we learned in chapter 8, okay? Which is the main idea in chapter 8 is how do you derive new types from old type using the data feature, okay? The data keyword, okay? It allows you to build, and it's actually an algebra, so we have the bar for the or the plus, and placing 2 types next to each other as the multiplication, the product. Okay, so let's go ahead and see how. I mean, we'll look at 2 detailed examples here: tautology checker and abstract machine. Okay, but before that, let's just complete this bookkeeping here. Small topic here on type classes and how you declare an instance of the type class. Okay, especially when you start defining your own types using the data mechanism, how will you include them in one of the existing type classes? Okay, it's important because otherwise you would have difficulty in showing. But so far we have used the default deriving show, a default method of converting a value to a string. But we may want to customize that, and that's why this will become useful. Okay. All right, so let's go to the basic examples. If you recall, in the type classes way back in chapter 2 or 3 somewhere, we had the EQ type class, okay, and class. So this is how it's actually defined, okay. So now we're getting into the nuts and bolts of how to define a type class, okay. Class EQ, and this takes up a type parameter, okay, A, where 2 operations are supported. Okay, for the EQ class, there should be 2 operators which must be supported. One is the equal, which allows you to compare 2 values whether they're equal to each other or not. And the other one is not equal to, which is written unusually with a / equal, okay, in Haskell. So those are the 2 operations which must be implemented by any type for it to become a member of this class, okay. So those are the 2 operations of equal to and not equal to, okay. And the signatures of those 2 should be A arrow bool, okay, where A is the type which you're comparing. So 2 A's you're comparing, 2 values of type A, and if they're equal, we need a true. If they're not equal, for the equal, if they're equal values, then true, and false otherwise. And similar for the not equal to, if they're not equal, then the true, else false. Okay, so those are the 2 operators, and these are the signatures. Okay, now of these 2 operators, one of them is already built in. Okay, the not equal to is already defined by EQ class. So if you want to build your own data type, okay, using the data mechanism, and you want to compare and you want to make it a member of the EQ class, then you don't have to worry too much about the not equal to, because it's already defined up there in the EQ class itself. Okay, all you have to do is define the equals. Okay. Anyway, you can see that this is basically passing the buck to equals. Okay, x not equal to y equals not of x equals y. Okay, so we're using the logic not, which is a built-in feature of it. Also is a function defined somewhere else. Okay, on Boolean values, and so we pass the buck. So how do you check for not equal to? Check for equal to, and then negate the value, right? If equals is true, then make it false. If it equals is false, make it true. Okay. So that's how an EQ class is defined. Okay. Now let's say that you want to make your class, or in this case the example we are showing is of bool. We want to show or make bool, okay, here, this bool here, uh, uh, an instance of this class. That is, we want the ability to compare Boolean values of true and false with equal to and not equal to. Okay. Now, this obviously is already built in, so this technically definition you don't have to do. This is already in the prelude, but we are showing how the prelude would have implemented it. Okay. So, and this is how you the syntax. Okay, you have to say instance, and then give the superclass or the class name of which you want to make an instance of. Okay, and then give the name of the class which or a type which you are building. Okay, in this case we are assuming we are building bool, but technically we don't have to build bool, it's already available. Okay, but assuming we are doing the work of the prelude, then bool is the type which we want to make as a member of the EQ class. Okay, that's why we say instance of EQ is bool, where clause, and then we write the implementation of equal equals. Okay, we have to give the implementation of equal equals. We don't have to worry about the not equal to, because that's handled by this definition there. Okay, so if you want to compare two Boolean values for equality, there's only four possibilities technically, right? False, 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 true, true, false, true, true. But we can make it a little bit more clever and compare the two equal values of false. Say false equals false equals true. So we are giving the definition when the two Boolean values you're comparing are false, both of them are false, then the EQ, the comparison must be true, right? The equal comparison must be true. And same way for true, true, both true is equal to true, right? So that's why we say true. And then we put the underscore here for anything else. And since we know there's only four possibilities, the other possibilities would be the other two possibilities. Okay, so false true and true false. Okay, in both those cases the answer should be false. Okay, so I mean you could have written out all the four equations, but it's not necessary, right? Using the wildcard mechanism, you can actually encode two of those last two equations into one equation like this. Okay, and we are taking advantage of the fact that these work top to bottom. So the false will be compared, and if they're equal, true, and we are done. We don't have to check for the other equations. Okay, and so on. Okay, so now by this definition, Prelude has made bool an element or an instance of the EQ class. Okay, which means you should be able to compare Boolean values anytime. Okay, all right. Now let's look at what we can do. Only types that are defined using the data or new type mechanisms can be made instances of class. Okay, so that's important. If you recall in the early part of this particular chapter, okay, we said that there are three mechanisms for defining new types. One is just a type, which is nothing but an alias, okay, and that's not very sophisticated. Okay, the second is data, using data, which is very sophisticated, and there is a special kind of data called new type. Okay, and that is such a special case that I don't even bother about it quite often. Okay, because it is a special case of data in which there's only one constructor and one input to that constructor. Okay, and in that case, the compiler has a way to optimize how some extra checks in compile time. Okay. Anyway, only data declarations, if you forget about the new type, can be made instances of classes. Okay, so obviously bool must be data. Okay, so data bool equals true or false. I think we saw this before. Okay, that's why we can make bool an instance of that. Okay, class. One more thing here, and classes can be extended to form new classes, very much like the subclass hierarchy kind of thing in object-orientedness. So, for example, we now know that EQ class exists, and it's got these two operators. Okay, and one example of instance of that is bool. There are many other examples and so on, which are examples of EQ, such as int and float. They're all examples of EQ because you can always compare two ints and two floats and so on. Okay. Now, the next class, which we studied a long time back in chapter 2 or 3, was the ORD, in which you can compare with other comparisons, less than, greater than, less than equal to, or greater than equal to, with those four comparisons and also the min-max. Okay, so there's additional operations which are supported in ORD in addition to the EQ. Okay, and this is how we write that extending the class. Okay, we'll say class EQA and then equal greater than sign ORD A. Okay, by that what we mean, we say that, oh, everything EQ. So EQ is a superclass in some sense from the object-oriented terminology, and ORD A is a subclass. Okay, And subclass inherits everything from the superclass, all the methods and all the variables, right? Instance variables and so on. Same idea here. Ord A will inherit all the operations of EQ. Okay, and then in addition there'll be some additional ones which are described here. Okay, so even though we don't describe double equals and not equals here in the but because we have extended EQ to ord A, those two operations, the double equals and then not equals, are actually available in ord. Okay, all right, what do these other six operations do? The usual stuff. I mean, these four will compare with that particular comparison and return a boolean true or false. Okay, so less than will say that, oh, a less than a, okay, one value of a less than another value of a. If that is indeed so, then true, otherwise false. Okay, so those are the four operations in addition to those two which will compare values. Okay, and since we can compare all the values in ord, we can also find the minimum and the maximum. By the way, the comparison, the ord is a linear order, a total order on all the elements, okay, which means that you should be able to sort all the items from the smallest to the largest, okay, which also means that we have a min and a max, okay. So A arrow A would be the signature of min and max given two A's. By the way, this is not all the min of all of it, but just comparing two items, okay? Basically the bigger and smaller of the two, that's what it is, okay? Which is a min of two elements, two values, okay? And what is a max of two values, okay? And the min and max are already implemented here. You can see that min xy with the guarded equation. If x is less than or equal to y, so the definition of min depends on these four. Okay, so we are using less than or equal to y, just like this not equal to dependent on equal to. Okay, same way, x less than or equal to y, then the minimum should be x, otherwise it should be y. And similarly, max of xy, if x less than or equal to y, then the max of those two would be y, otherwise it will be x. Okay, so min and max are already defined in the ord class. So if you want to define a new class like bool, let's say, okay, which is defined using the data keyword, and you want to make it a member of the ord class. Previously we made it a member of the EQ class. Now we are making it a member of the ord class. Okay, so we'll say instance ord bool where, and all we have to do is give the definitions of these four guys. Okay, these four operators. Okay, so first we'll do the less than. Okay, so false less than true equals true, and any other comparison, the other three comparisons will be false. Okay, again, because we have two values we are comparing, there are four possibilities: false, 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 true, true, false, true, true. Okay, now here we are making an implicit assumption that false is less than true. Now that's interesting. Okay, why is false less than true? Why can't true be less than false? Okay, now it seems like an arbitrary decision. Okay, and actually it probably is arbitrary when you look at it from one point of view. Okay, you have two values in the bool, and you want to compare these two values with less than. You want to say which one is smaller, which one is bigger of the two values. Okay, now obviously you can say that false is smaller, true is bigger, or you can say true is smaller and false is bigger. Okay, of these two you have to choose one, you cannot choose both, right? Now, I think for many other reasons, I think even if you go back to your Java and C and so on, you would, based on also the fact that false happens to be the identity for the OR operator, and true, there are some really philosophical as well as some really technical reasons why false should be less than true. Okay, and even in C and so on, zero value is treated as false and non-zero value is treated as true, right? A positive non-value, I'm not sure about negative, but certainly if a positive value is treated as true, which is so that's why false is less than true. Okay, so no matter what, we have to choose one, and this is the right choice. Okay, and any other combination, false less than false, true less than true, true less than false, all those three are false. Okay, only false is less than true. The other comparisons of everything else is false. Okay, so we have successfully defined the less than. Now we've got to successfully define these guys, but these guys can be defined, for example, b less than equal to c, b greater than c, and b greater than equal to c can be defined in terms of this less than. For example, b greater than c must be equal to c less than b. Okay, the other way around. If b is greater than c, c must be less than b, right? And less than equal to would be an OR of less than and equal to. Okay, So, and then greater than equal to is the opposite of or equal to C, less than equal to B. Okay. So using the other operators, you can actually define these three comparisons for the booleans. Okay. So anyway, this part gives you how you can include bool as a member of the ORD class. Okay. So you got to implement those. Okay. So we are learning a little bit on what happened here. Maybe we didn't run the previous cell. Yeah, there you go. Okay, so we learned how to make a new data type a member of an existing class. Okay. Now, one other thing is that suppose you don't care too much about, I mean, not care. I mean, you're not bothered too much about implementing some of these things. You can actually specify deriving clause. Now, this is the first time we are actually learning about it. We've already used it. Okay. So when new types are declared, it is usually appropriate to make them instances of a number of built-in classes using the deriving clause. Okay. So let's say that we say data bool equals false or true. So that's how you'll define bool. Okay. Notice that we said false or true. We did not say true or false. And that is actually significant because in the ORD, in the deriving class, when we use the deriving class, Haskell automatically picks an ordering for the values. Okay, it goes left to right on these options. Okay, so automatically it'll choose false to be less than true. Okay, and so on. Okay, so anyway, that's besides the point here. What we're trying to learn here is that when we define a new data type like that, it's customary, okay, not necessary, but customary to include this deriving clause next to it. Okay, deriving, and in parentheses make a list of all the built-in classes which you have learned of. There's about 7 of those we learned earlier on. Okay, these are the built-in, but if you get sophisticated, you can write your own class definition and then include other types into that. Okay, but EQ, ORD, show, and read are the 4 type classes we learned. There are a couple more, but these 4 are quite commonly used. So you do that. Okay. So once you do this deriving, then these kind of definitions are automatically built in for you. Okay. Automatically taken care of. So you don't have to do that. Okay. So when you define a new data type using the data keyword, now bool, of course, we just saw that, but something new. Then when you just say deriving, then this Haskell has a way to automatically implement those methods for you. Okay. Okay. Anyway, now because we included bool as a member of the EQ class, we can say false equals false, false less than true, show false, and read false colon bool. We can do all of those because the bool has become a member of these 4 classes just by saying deriving that. Okay, so you can actually compare all of these. So false equals false should give us true, right? False less than true should give us true. Why? Because we put false before true in this choice. Okay, that's why. Show false, it will convert it automatically to a string. Okay, and read false colon boolean will convert this into a boolean value. Okay, anyway, this last one colon is necessary because the read function, okay, it takes a string and makes it into a value. But if you don't give the colon bool, it doesn't know that this is a boolean value. It might get confused, Haskell, that is. See, so that's why you would have to specify the colon type here. Okay, otherwise it doesn't know what type it needs to convert false into. Okay, false by specifying bool, it converts it into bool. Okay. Of course, if you misspell this and say colon bool, it'll give an error because it won't be able to convert the misspelling of false. Okay. Okay. This point is again just the same thing which I just mentioned, is that for the purposes of deriving instances of ORD type, when you deriving ORD, then the constructors, the ordering of the constructors of the type is determined by the position of in the declaration. Okay, because false was placed before true, false will be less than true. Okay. And in case of constructors that have arguments like here, okay, like remember this example, circle float and rectangle float, and you could say deriving at the end of it and say ORD. Or here's another example where just a and then nothing. Okay, here also we have a type here next to it. Okay, so if you say deriving at the end of it with ORD, okay, or maybe even equality. So let's take this data shape and say deriving equal, ORD, and show. Then when you compare two rectangles by providing values here and here, you might wonder how do these two rectangles compare with each other, okay? And the default, because we just said deriving, we didn't tell how to compare them, right? So rectangle will be compared with rectangle as follows, left to right. So it'll look at the rectangle, oh, they are the same. Then it'll go to the next one. Oh, that's a 1.0 and this is a 2.0. Oh, 1.0 is less than 2.0. Oh, it's not equal to, right? 1.0 is not equal to 2.0, and it'll stop there and say, yeah, these two cannot be equal, okay? And then say false, okay? It will ignore these values here, okay? And similarly, rectangle 1 and 4 greater than rectangle 2 and 3 will be false. Why? Because rectangle and rectangle is the same. 1 is not greater than 2, that's why you got false, and you stop there, okay? Circle 3.6 equals circle 5.5 will also be false, because even though circles are the same, but 3.6 and 5.5 are not the same, okay? And here's another example for show, okay? So the comparisons, when you do the deriving class, okay, there is a default mechanism which Haskell uses, and if you can play around, you can get used to. It's basically the lexicographic, okay, that's really what it is. It is lexicographic on the constructor name as well as the values which appear after that, like these guys, okay? All right, so I think we are done the bookkeeping of this minor small topic here before we get to the two big examples, okay? And the first example is called the tautology checker. So let's look at this, okay? It's a little bit involved, it goes a little bit, okay, but 7-8 functions, okay? But it's an interesting one, okay? And this is discrete math, okay? Remember from discrete math, we have a language of proposition logic. And what is it? A proposition logic is made up of the two Boolean values, false and true, and also variables, A, B, C, D, like that, okay? Which each of these variables correspond to a Boolean value, okay? So when you say P and Q, P is a Boolean variable, Q is a Boolean variable, and P and Q both can have a value of true or false, and we have an AND operator in between, okay? So we have this, in this project or a mini project, we're going to allow variables, we're going to allow these two base values, and we're going to allow these three operations, okay? We'll not do the OR, but we'll do the NOT, and implies. Remember, P implies Q from discrete math, so we'll allow that, okay? So we are going to allow only these three, and of course we can parenthesize expressions if we have to, okay? And yeah, so here are some examples, okay, of those things there, okay, of the type of expressions we're going to deal with, okay. We're going to deal with propositional expressions, okay. Here's an example, A and not A, okay. Now this is basic logic, okay, from your discrete math, okay. The other one is A and B implies A. That's how you write it, okay. And the next one is A implies A and B, okay. And the next one is A and A implies B, okay. So these are all valid, well-formed expressions in this example project, okay. So this is a mini project we're doing that, okay. And the meaning of and, not, and implies you should know from discrete math, okay. Basically the truth tables for those three operations, okay. All right, so what we want to do is, given a formula like this, okay, any one of these guys, given any one of these formulas or anything new you can create out of variables, x, y, z, a, b, it doesn't have to be a and b, you can use any variables, okay. We'll assume the, I guess, the a through z letters, okay, capital A through z we'll use, okay. We'll see whether there's flexibility in using other combinations and so on, okay. Anyway, so our step one is to define a data type, okay, and we're going to call it prop, P-R-O-P, okay, prop for proposition, okay, propositional logic formula, okay. Data prop equals, and we are going to say that it is one of 1, 2, 3, 4, 5. So we're going to say there are 5 possibilities here, okay. There are 5 types of prop, okay. Maybe a better way to indent this probably is like that, okay, so that we have all the 5 listed here one below the other, okay. So that's your declaration. Now let's see what are these 5, okay. The first one, and also we're going to make use of our built-in bool so that we don't have to invent these true and false in our higher level language we are trying to build. Okay, so we'll actually use the default Boolean values of true and false of Haskell in this new language we are defining. Okay, or new type we are defining. Data prop equals const. So we'll say const, and then here we can actually have a bool, which means a true or a false. Okay, so we'll have to say const and then a true or const false. Okay, and then if it is a variable like ABC, then we'll say it's var. Okay, that's our constructor, and then we will have a character. Okay, here we see. So technically we can allow lowercase characters also for these variables, and even plus minus and so on. We'll try to avoid those, but let's assume we'll just use the capital letters ABC. Okay, so var and then char. Okay, so that would be how you declare a variable. Okay, in this propositional language. Okay, false, true, we are going to use the const and the bool. And then for the three operations of not, and or, we'll use these three constructors, not, and, imply. And not takes one propositional formula, and takes two, and imply takes two, right? Imply to the left hand side of the arrow and right hand side of the arrow. Okay, and we'll say deriving show in all of them, so that at least we can print these guys. Okay, on this terminal or in the Jupyter lab. Okay, so that is, we can convert a value of type prop into a string using the show. Okay, all right. Now we don't need to define a parenthesized expression here. Why? We can use the inbuilt Haskell parenthesis around these guys. Okay, because Haskell provides a parenthesis, right, which you can put around any value, including values of type prop. Okay, so that's why we don't have to include. Now this looks like a grammar of what we have been doing in the early part of this class. Okay, it is a grammar. Okay, it's actually a very nice grammar which introduces these operations prefix, not, and imply. Okay, and even in homework 1 we might have used the and or not in our logic or in our Lisp expressions, if you remember. Okay, so in some sense this data has the ability of a grammar. Okay, a context-free grammar to create new types of expressions out of old. Okay, all right. So we don't have a separate rule for parentheses because we can use the inbuilt parentheses of Haskell. Okay. All right. So now let's see, with this data type, can we code these four examples? Yes, we can, and they're coded below here. Okay, in the next cell. So let me go here, go there. So when I say p1 colon colon prop, p1 is a variable, Haskell variable, and its value is going to be one of the values of this data type. Okay, and I want to take the first one and code it. I'll say and, because there's an and between two things here, so you need to know how to parse this inside out. Okay, and then the first one is an a, so I'll say var a for that. Okay, because that's how you define a variable in this higher level language. And the right hand side of this is not a. So I have to give the second expression, because in and you have to say prop, right? So the first prop is the var a, and the second prop is the not var a. Okay, it's an and of a and not a, right? So those are the two things which are across the and. Now here we put the and in the front because it's a prefix notation we are using. Okay, and the constructors must be in the front, right? So we have and var a, not var a. Okay, so this is the right way to write this expression for p1. Okay. And similarly for the second one, you can see that the implies is at a higher level, and then the and must happen first because of the parentheses. So that's why you can see that there's an imply, and this whole thing is and AB. Okay, and var A var B, and then the second right hand side of the implication is A. Not okay, so var A. Okay, anytime you have A here, you have to put var A here in the data. Okay. And similarly for the third one, imply var A and then the and of var A var B, okay, to take care of the A and B here. Okay, and the fourth one a little bit more complicated. It's an imply at the top level. On the right side is the var B, imply here, and then on the left side of the implication is this whole thing, which is an and. So that's why you see the and first, and then this is a, so it'll just become a var A here. And this is an implies A or a B, so this will be imply var A var B. Okay, so that's how you construct these values. Okay, there you go. And then if I want to show these guys, because I said deriving show, so I can actually print them. So here you go, I took the p4 and showed it, and it printed exactly what I had there. Okay, because this is the default print. Okay, now if you want to print it with differently, and if you want to print it like this, okay, A parenthesis A, and then you cannot say deriving show, you have to write your own show method for this data. Okay, and which you can do that using the mechanisms we learned here, okay, up there, okay. So this is how you make the prop a member of the show class, okay, but here we are using the default ones, okay. All right, so we are done with the first step of this project, and that is we have a mechanism to create values uh, of type prop, okay, which will correspond to our Boolean expressions. These are called Boolean expressions, or propositional expressions. That's a better way to call them, okay, from proposition logic, okay. All right, so the next step is, now, okay, before we go to the next step, let's just recall what we are trying to do here, okay. What we're trying to do here is a tautology checker, okay. What does that mean? That means that given a formula, I want to say yes or no. Yes, if it is a tautology. You must know what a tautology means, okay. Tautology means it's always true, okay. And no, it's not a tautology, means it's not always true, okay. What do you think about A and not A, okay? Is that a tautology? No way, okay. It's actually A and not A would always be false, okay, no matter what A is, okay. And the way you verify whether something is a tautology or not is to draw the truth table for the formula, okay, and then see whether the value of the formula is always true, okay. If a formula is always true, no matter what values you give for the variables in it, okay, then it's a tautology. Tautology means always true, okay. So that's what we're trying to figure out, okay. Given a formula, can we check whether it's a tautology or not, okay. So that's the program we're trying to write, okay. So now coming back to this, how can you check whether a formula is a tautology or not? What you have to do is you have to look at, let's go back to this example, okay. Let's look at this last example, okay. This particular, if you want to prove whether, or you want to test whether it's a tautology or not, the way to do this is to draw the truth table for this, okay. And in the truth table, this expression will be on the rightmost side, okay. If you want, I can show you here. Copy this one here, okay. Yeah, go down here somewhere, okay. Yeah, so that's that. So the truth table for that would be something like this, okay. This is the header, okay. This is the header of your table, truth table. And here we have the four possibilities: false, I'll just use F for false, okay, false, 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 true, true, false, and true, true, right? These are the four possible values for the two variables, okay. So if you have two variables, you have four possibilities. If you have three variables, you'll have 8 possibilities. So in general, this is actually 2 to the power n, so it's a very serious problem, okay, exponential. Anyway, don't worry about the exponential nature of this. So what you do is that, okay, if it's false and false, then you'll calculate the value of this, okay, whatever it is, you have to calculate. A is false, and B is false, and B is false. So you'll have to go and apply the rules of implication and ands, and you have to calculate the values for this formula under each of these is sometimes referred to as an interpretation for these variables, okay. Under each of these interpretations, you have to find the value, okay, and you'll get a true or false. And if you got true in all of these rows, true, 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 then it's a tautology. Otherwise, it's not, okay. So that's really what we are trying to get at, okay. So there is so the whole problem of checking whether the formula is tautology or not can be broken down into 2 steps, okay. Step 1, generate all, let me call that interpretations. That's the term, okay, used for each of the rows, okay. The false, false is one interpretation, false, true, so on. And then step 2, oh, I forgot the one here, okay. Step 2 would be check value of formula, of propositional formula in the interpretation, okay. All right, check and check whether it's true or false, and you have to keep getting truths in all the interpretations. In each, let's call this each, okay. So those are the 2 steps, okay, 2 different steps. Now we're going to tackle the second step first, okay, here, okay. So let's come down here. So what we're going to do is, because you can think of each interpretation as a dictionary which assigns to the variable a Boolean value. Okay, A is false, B is true, right? So in that sense, it's an associative array or a dictionary. Okay, it given the variables, it tells you what value it is, true or false. Okay, that's called a substitution. Sometimes you call. Okay, so this interpretation can also be thought of as a substitution. Substitution of Boolean values true and false for each of the variables. Okay, so we'll tackle the second problem first. We'll define substitutions and how to evaluate a prop value in a substitution. Okay, here it is, and actually it's pretty straightforward. So it's just a couple of functions we need to write. Okay, so we'll take type assoc kv equals a list of key value pairs. Remember this, actually we did this earlier. Okay, so exactly same thing. Okay, and we also wrote this find. I'm just repeating it here. Okay, I'm repeating that find here. Okay, remember we had to go find for a key and find out what its value is. Okay, so that's what find does. Given an associative value associative list which contains a key value pairs, and given a key k, it'll tell you what value it is, and we'll assume there's only one value for each, so we don't have the problem of more than one value. Okay, and head will give us that. Okay, so this assoc kv would be the substitutions. Okay, so given a substitution, so for example, here's a substitution. Okay, yeah, substitution will be an example of this associative kv. Okay, it'll be a value like that. Okay, it's a data type is associative kv. Okay, so here's an example. A gets a value false and B gets a value true. Okay, and that one is actually the this one here, the third row. Okay, no, A false, this one, second row. Okay. So that's how the substitutions will look like. Okay, which is actually a value of this type, associative kv. Okay, so you can see that we said the type substitute equals associative char and boolean. Now we had to instantiate the k to be char and v to be bool. Why? Because our propositional variables are char, and the actual value for the propositional variables is a bool. So that's why our type substitution would be an associative list of char and bools. Okay, so here's an example. If this was our substitution, which assigns the value false to A and true to B, then we can think of an eval function which takes a substitution and a proposition formula and tells you whether it's true or false. The formula, that is, whether this whole formula is true or false in a given substitution. Okay, and that's what basically applying the values for true and or nots. Okay. Are the meanings of the and implies and nots. Okay, all right, and this is actually a very simple function because we can actually pass the buck to the Haskell's and not and so on and so forth. Okay, so this is the signature eval, takes a substitution and a proposition as input and returns a true or false for that. Okay, now if the proposition, so the recursion is on the proposition now, it's not on the substitution. Substitution is given to us, it's fixed. Okay, proposition is the recursive variable now. Okay, so and we know that the proposition is one of 5 types here: constant, var, not, and an imply, right? So we write those 5 cases here: constant b, var x, not p, and pq, imply pq. Okay, so those are the 5 ways you can have a proposition. Okay, and what would be the value of const b? Now the return value must be a boolean for these guys. Okay, obviously we don't care about the substitution. The b itself is a boolean value, right? The const next to the const is a boolean value, and that's the value of a const b. Okay, if you say const false, the value is false. Const true, the value is true. Okay, now what is the value of var x in this substitution s? Okay, that would be to find x in s. Okay, right? Because you have to go find what is this value in the for example, if I say in this substitution, what is the value of a, okay, variable a, it'll be false. What about the value of b? It'll be true. Okay, so you have to go find it. So that's why we call find xs in that. Okay, find this variable x in the s, and the boolean value will be returned, and that's what is the value here. Okay, and what is the value for not p? It'll be not the Haskell not of the recursive call on p. Okay, and similarly for and, it'll be the Haskell and of the recursive call on the p and the recursive call on q. And imply would be Yeah, that's interesting. What so you'll have to evaluate the two, yeah, the two values, the p and the q, and we sort of use a trick here, less than equal to, okay, because these are Boolean values. I can say less than equal to. Why would that be true? Because the implication is true only when p is true and q is false. Excuse me, the other way around. Okay, so if you go back to the truth table for implies, p implies q is true, excuse me, is false only when p is true and q is false. Okay, that's the only case of the four cases. Okay, that's the only case when it is false. In the other three cases it is true. Okay, now if we did this, and here this is the antecedent of the imply, and this is the consequent of the imply, and if you just compare the Boolean values, okay, if this is false, okay, if the left hand side is false, if the p is false, then this automatically is true. This whole thing is true, right? And if you say false less than equal to, so I don't care what this value is, false is always less than equal to true, and false is also less than equal to false, right? So this whole thing will become true in that case. So we are using the fact that false is less than true to actually implement implies. Okay, anyway, think about it, but this is the right solution here. Okay, you could also have said I think something like this. Okay, if eval sp, if that returns true, okay, and you could say that, I guess you may need some parentheses, okay, but and eval sq is false, okay, and you'll say not in front of it, right? I guess you need some parentheses. I'm not putting that. Then the answer should be false, right? Else true, right? So that's you can actually encode it that way, but it's not a problem. Okay, you can do that, but this is equivalent to that. Okay. Anyway, here we have an eval, okay, which calculates the values of complicated propositions like these guys, the values of these, given the values of a and b and so on. Okay, and those values of a's and b's are available in the substitution in this value. Okay, in this type value. Okay. That's it. So we have actually done step, actually say step 2 here, which interestingly matches the step 2 of this what we want to do. So given a formula, proposition formula, and given a substitution, okay, or an interpretation, okay, given a substitution, we can check whether it's true or false. Okay, the eval whether it's true or false. So here, let's go ahead and run this cell and run this cell. So a, given the fact that a is false and b is true, what will be the value of p2? Now we have to go back to p2. P2 was it's even better here, a and b arrow a, right? So if you find the value for a and b value arrow a and b would be false, right? Because a is false, b is true, so false and true will be false. False arrow something will be just the true, right? Because false on the left hand side of an arrow in the implication will make the implication true. Okay, so that's why p2 is true, and so on. You can test this out. This one is false. Now you can also change the Boolean values here, maybe make this true and see what happens, and so on. Okay, so you can play around with this. So we have now a mechanism which, given a substitution and given a propositional formula which is made up using these rules here, using this data type, we can calculate the value true and false. Okay. Now we get to the first part, which is a little bit more trickier, and that is to generate all interpretations. That is all these combinations. Okay, all these combinations, and that's a little tricky. Okay, because this is 2 to the power n. The number of possibilities are too many. Okay, so let's see how to generate those propositions. Okay. The first step would be to find all the variables in it. Okay, correct? Because and also some variables appear more than once, right? Like in this case, in some of these formulas, in this last one, a appears twice and b appears twice. Okay, so we really need all the variables, but also we need to know how many unique ones are there. Okay, so that's probably the first step. Okay, so now let's see what to do here. How do we get that? Okay, here's a function called vars, which will, given a proposition, it'll give us a string or a list of characters, all the variables in it. Okay. And right now we'll not worry about the duplications. Okay. So we'll just collect all the variables. Okay. And it's a simple one. Okay. If you have a const, there's no variable here, right? So the answer should be the empty list. Okay. If it's var x, then obviously we are looking at a variable x, so that will be the answer, because we are trying to collect all the variables, right? And if it's a not p, then all the variables in p would be the variables in not p. Okay, so there you go, vars of p. So it's a recursive call. And if it's an and or implies, in both these cases, it will be all the variables in p plus all the variables in Q, because we are just accumulating all the variables. We're not worried about the actual meaning of these guys here. Okay, I think we saw something similar in homework 2. Okay, anyway, it'll be vars p plus vars Q. Okay, in both these cases. Okay, so this is how you would calculate the variables. Okay, so let's go ahead and run this, and let's find the variables in p1, p2, p3, p4. Okay, these 4 guys. Maybe it's a good idea for me to copy these 4 here, because I'm going back and forth too much there. Okay, so those 4 examples are there, p1, p2, p3, p4. Okay, all right, so we are here, variables, right, around this cell, and then I want to check the variables in p1, p2, p3, p4. Okay, remember in p1 I should just get the a, even though it's twice. Okay, and then the ab, ab, ab. There are different occurrences. Okay, so here you go. When I run this cell, I get a twice in p1, ab, a in p2. Oh, this should be p3, I think so. Yeah, AB in P3 and AABB in P4. Okay. Now we'll get rid of the duplicates later. Don't worry about it. Okay, because we are doing this bit by bit. Okay. Now the next. Okay, remember what is our step here? We want to generate all these, all possibilities of the possible values for all the variables. Okay. These are called the substitutions, or these are called interpretations. Okay. Let's call it substitutions, because that's what we are using right now. Okay. So we got the variables. Okay, so we really need a function which generates all combinations of false and true for n variables. Okay, and in general, it is 2 to the power n, the number of combinations of false and true for n variables. Okay, if you had one variable, let's call it a, it can be true or false, so only 2 values, right? If you have 2 variables, then it's false, 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 true, true, false, true, true. Okay, 4 possibilities, and so on. If you have 3 variables, 8, and so on. Okay, here's a function which I think it's called bools 1. Okay, yeah, that's right. Which will given a number, it will give you, and this number would be the number of variables. Okay, will give you all the possibilities, all the 2 to the power 3 possibilities here. Okay, so let's look at this function before we look at how it works on this particular number 3. Okay, so the idea here would be, remember we earlier I think in the previous chapter we used the int to bin, or maybe it was earlier in this chapter. Given a number, integer number, let's say 3, 4, 5, or whatever it is. Okay, we can convert it into a binary sequence of zeros and ones. Technically, this false and true are nothing but binary, right? Zeros and ones. So that's why we can use a bit pattern for the number n, for which we are trying to find, where n is the number of variables for which we are trying to find all the possible substitutions. Okay, we can convert the number into a number of variables into a bit pattern of zeros and ones, basically convert it into binary. Okay, in a list of bits. Okay, and we have seen this. Okay, int to bin of 0 would be the empty list of binary, and for n it will be n mod 2 and n div 2, and recursive call on the n div 2. Okay, and the n mod 2 is cons in this. Okay, so the n mod 2 would be 0 or 1, and that will be const in front of this. Okay, when you do cons in front, then you would I think you'd get in the right order, right? Actually, in our case, the order really doesn't matter, right? Because we don't care whether 100 is 4 or 001 is 4, right? Because we want the different combinations of zeros and ones there. Okay. Anyway, so whether we are consing or whether we're adding at the end should not matter. Okay. Anyway, so this is the function we have seen before, which takes a number and converts it into a sequence of zeros and ones, and that zeros and ones is the binary representation of that number. Okay, so the number is int. Okay, and also the bit itself, which is a 0 or 1, we define it to be int, okay, but it'll only be 0 or 1, okay. And so this function, what it does is that it, given a number, it converts it. So given the number 3, it'll convert it into um, 1 1, right? 1 1 is the 3. If it was 8, it'll be 1 0 0 0, okay, and so on, okay. That's what this does, okay. And bools, what it does is that it takes an integer and makes a call to this into bin. You'll see that here, okay. And then what it does is that it converts a zeros to a false and 1 to a true, okay. We will see, and that's how it constructs this particular list of all the possible substitutions for the 3 variables or 4 variables or whatever it is, okay. So let's if you understand into bin, it just converts a number into its binary version, okay. Let's look at the bools. What it's supposed to do? Bools 1 is supposed to take a number, okay, which is the number of variables in your formula, and return a list of bools, okay. Why a list of bools? Because each list of bools is actually one substitution, okay. So for example, false 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 is one substitution where a gets, the first variable gets false, the second variable gets false, the third variable gets false, and so on, okay. All combinations we want to get, okay. Now let's look at the bools 1 n. N is input, okay, and here's her final answer. We're making use of compositions and so on and so forth. Let's see what's happening here, okay. This looks like magic, but that's what it is, and that's what Haskell is, okay. So we have to look at this from right to left, okay. And actually, in this case, it's not that terribly complicated, because all we're doing is we're mapping with this function on this, okay. So assuming range is a list, we are applying this function, which is specified here, to each element in the range, okay. So we'll come to this function later, but let's see what range is, okay. Range is a list, given the n, it's a list going from 0 to 2 to the power n minus 1, okay. And that's exactly the bit patterns for n, right? So for example, if n was 3, okay, let me go down here. If n was 3, the range, this particular range would be 0, 1, 2, 3, 4, 5, 6, and 7, okay. Why? 2 to the power 3 minus 1 is 7, right? 8 minus 1, 7, and it'll list all these numbers here. And our idea is this one would will convert it to 0, 0, 0, okay. 1 will convert it to 0, 0, 1, and so on. We're going to convert each one of those elements in the range to a 3-bit pattern, okay. And then the zeros will go to a false and 1 will go to a true, and that's how we get that list, okay. So any questions on the range? No, right? So range equals 0 up to 2 to the n minus 1, okay. So these are just numbers, 0, 1, 2, 3, 4, 5, 6, up to 7, let's say, okay. Then the next one, make n bs, what it does is that it takes the bits, which is probably obtained from the range, okay, like a 0, 0, 0. Oh, okay. No, we don't know where it comes from, but let's say it's a list of the bit patterns of any one of those numbers, okay. Let's say 110 or something like that, okay. Because this into bin might generate bit patterns which are not of uniform length, correct? Because if n was 2, it'll just generate 1 0. If n was 10, it'll generate 1 0 1 0, okay, which is 4 bits versus 2 bits for 2, right? So the variability is there in the length, and that's what make n does. It makes them all uniform by padding them with zeros in the front, I guess, or in this case at the end, okay. Yeah, actually, technically, it doesn't matter in which. I guess it adds at the end, and then there's a reverse happening. So those zeros show up in the front. Okay. So make n bs. What it does is that given a bs, which is a bit pattern, bit stream, let's say bs, zeros and ones, a list of zeros and ones, and given the n, which is the length of the bit pattern, okay, which will be equal to the n of the original one here, okay, right? Because that's our 2 to the n minus 1 can be represented in n bits, right? So that's the idea there. So, and this we have seen. We take the BS, the bit pattern, and attach a bunch of zeros. Repeat 0 is infinite zeros. We attach a bunch of zeros at the end, and we take n bits in front of it, from the front of it. Okay. So this will make all the bit patterns uniform length. Okay. and convert 0 converts a 0 to a false, okay, and convert 1 converts 1 to a true, okay. So you understood these 4, okay. So now let's see what's happening here, okay. Range is our 0 to this one here, 0 to each of these numbers, okay, uh, based on the 2 to the power n minus 1, okay, up to that. And we're going to apply this function to each one of those, okay. And because this function is a composition of 4 things, we'll have to do this right to left, okay. Composition happens right to left. So what we'll do is take each number in the range, convert it into a bit pattern, okay. So for example, if the number was 2, we'll get 1 0. If the number was 10, we'll get 1 0 1 0. But because they're all of different lengths, we'll do a make n on the output of into bin. So when we say make n on the output of into bin, we will get uniform length bit sequences of bits in a list, okay. Then we'll apply map convert to it, convert 0 to a false, 1 to do. We'll map that to each bit inside that inside this list, okay. And then we'll reverse it, okay. The reason we reverse it is because we were adding the zeros at the end, okay. And actually this guy will probably when you attach the ones here, we actually get in the reverse order, okay. So now we are being true to the actual value by reversing it here, okay. And when we reverse it, we will get the bit patterns. Actually now it's not bit pattern anymore, it's a sequence of booleans now, because after you apply map convert, it becomes booleans, okay. And then you reverse it to get the right boolean sequence, okay. So but you have to do this on each item in the range, okay. So let's do this, okay. Let's run this and run that. You see that bools 1 of 3 gives me the 8 possibilities. If I change this to 4, I'll get 16 possibilities, each containing 4 values. You see that 4 4 and so on, okay. So this is a nice way to generate all the Boolean substitutions for all the variables, okay, given n, where n is the number of variables, okay. Okay, maybe the video is getting long, so we'll stop here and we'll do one more video, hopefully a short one, because this project is almost done and the second abstract machine is pretty small. So I think let's stop here and we'll do another video to wrap this chapter 8, right? Okay. See you soon.